Good morning, good afternoon, good evening. We are back and better than ever. This is The Cure. The Cure is calculus, and this certainly is just like heaven because of the calculus. We are talking about inflections and shape part 3. Let's get right to it, shall we? The ultimate objective again is to be able to sketch curves. So here we go. We have considered this function here, and basically we're going to sketch it using calculus, using what we have learned. And I'm not going to necessarily follow these steps in the order um, that they are given. Okay, so let's find the first derivative. And the first derivative is going to be, let's see, 12x cubed minus 48x squared plus, let's see, 48x. Yes, oops, 48x. Okay, and let's see. We are going to factor that and set it equal to 0. I think I can factor out a 12x, and I am left with x squared minus 4x plus 4, and we'll set that equal to 0. And let's see, that's going to be 12x times x minus 2, the quantity squared, equal to 0. So that gives me x equal to 0 and x equal to 2. So let's do a first derivative sine diagram. I'll do it right here. So this is f prime, and we're going to have that at 0 and at 2. And of course we would choose points in these intervals. And without wasting time, I will say, because I know you know how to do that, minus, plus, plus. Okay? And right away, that tells me that in this interval, the function is increasing. I'm sorry, no, that's a minus, so it's decreasing, increasing, and increasing. So here it says find the intervals where the function is increasing or decreasing. We have done that, so we can say it's increasing for, let's see, x greater than or equal to 0, because this is not an asymptote, so we don't have to worry about the domain being restricted. And it is decreasing for x less than or equal to 0. So there, very good. Okay, now let's find the second derivative, and I'm going to find the second derivative using the first form of my first derivative. So the second derivative is going to be, let's see, 36x squared minus 96x plus 48. Okay, and I'm going to set that equal to 0, and I think, let's see, we can factor out a 12. Is that fair? So I'm going to say 12 multiplied by 3x squared minus 8x plus 4 equal to 0. So the 12 becomes irrelevant when we're looking for our zeros or our critical points. And if we factored this, it would factor nicely into x minus 2 times 3x minus 2. And you know how to factor, so I'm not going to go over that, which gives me x equal to 2 or x equal to 2/3. So I'll do a little sine diagram for my second derivative, and that is going to be, let's see, 2/3 and 2. And checking, choosing some values on these intervals, substituting back into the second derivative, I get a sine diagram that looks like this, plus, minus, plus. So that tells me that on this interval, the let's see, the shape of the curve is concave up, concave down, and then concave up right there. Okay, so let's see. The point 2, I will tell you, if we put 2 back in here, we get the point 2, let's see, 2, 7, sorry. If I replace x with 2 here, I get 2, 7. What else? We get 0, that's easy, negative 9. Okay, and if we put in 2/3, I will tell you you get negative 2.48 or about negative 2.5. Okay, so let's plot those points. So let's see, 2, 7. Let's see, so let's make this 7, 7, and 2. So that's right here. And 0, let's see, we'll put negative 9 about here. So we have a point here. And what else do we have? We have 2/3, negative 2.48. I'm going to put this 2 a little bit further out there. Oops. Let me get rid of that. Okay. So I am going to, let me get rid of that without messing up my nifty graph there. Okay. I'm just going to put a little bit further out. 2, 7. And then so 2/3, negative 2.48, that would see, this would be about 1, so 2/3 negative, maybe about right there. And what's happening at these places? Well, let's see, we know that the function is decreasing, yes. So here we're decreasing and increasing, so we have a local min right here at 0, negative 9, so I know I have this, okay. Then we're increasing and increasing. I know I'm concave up, concave down, concave up. So I know I have a point of inflection here. So I got to be a little careful because it's going to even out here and then go back up like that and like that. Okay? And I should have been a little bit better. Let me do that point again because I know that it becomes concave down to the point 2/3 negative 2.48. Okay, so there you have a neat little graph there. And let's just take a look at the Inspire and get a much better look at the graph. And you can see that we did pretty well. Concave up, then concave down, then concave up at our point of inflection, decreasing, 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 and increasing the rest of the way. Okay, next example, let me go back here. Same thing. Consider this function, find the x-intercept. This one I am going to do step by step, and this is just sort of guiding you on how you can how you can approach graphing these. To find the x-intercept, I let y equals 0. Yes, so that would be 0 equals 2 minus e to the negative x. Yes, and so what would we get? We would get e to the negative x equals 2 if I keep everything positive. And let's see, we take the natural log of both sides. Natural log e to the negative x equals natural log of 2. So negative x, natural log of e equals natural log of 2. Yes, but the natural log of e is equal to 1. So I get negative x equals natural log of 2, or x equals negative natural log of 2. Which I will tell you is approximately equal to negative 0.693. So we'll put that in our pocket. B, find the y-intercept. That's a lot easier because I just let x equal 0. So y would equal 2 minus e to the 0, which is 1. So y would equal 1. So the y-intercept is at 1. Okay, and show algebraically that the function is increasing for all x. Well, that's really algebra and calculus. So for C, I'm going to find dy dx, okay, and dy dx is going to be equal to, derivative of 2 is 0, derivative of negative e to the x is negative e to the negative x, times the derivative of negative x is negative 1, so that's going to be e to the negative x. Yes? Okay, well, what do we know about e to the negative x? E to the negative x is equal to 1 over e to the x, yes. And I need a little bit of room here so we don't get confused. And we know that e to the x is greater than 0 for all x. This is a symbol for all, by the way, for all x. Therefore, dy dx must be greater than 0 for all x. And if it's greater than 0, then the function is increasing, right? The first derivative tells you where the function is increasing. So that is a way to prove it not using a sine diagram. Okay. What about D? Show algebraically that the function is concave down for all x. So I need the second derivative. So the second derivative, and I'm going to use, let's see, this form right here to take the second derivative, the derivative of the first derivative. And that is going to be e to the negative x times negative 1, which is negative e to the negative x. Well, by the same reasoning, well, this is going to equal negative 1 over e to the x. And e to the x is greater than 0 for all x, which clearly implies that the second derivative is going to be less than 0, because 1 over a positive is a positive, multiplied by a negative is a negative, and that is going to be for all x, which implies, and I didn't do that here, you don't have to, that it's concave down for all x. That I would say y is concave down for all x. So we've done all that. Use technology to help graph y equals 2e to the negative x. Well, let's just try and sketch it here. Negative 0.693. If this is 1, then that would be about right here. The y-intercept is 1. It's about right here. Let's see. We're not going to the graph of e to the x is going to have a vertical asymptote. And it's going to go 1 from here. So we're going to go through there. And we know that it's increasing like that. There we go. So something like that. Okay, let's check the technology. We'll go to the next graph. And there it is. X-intercept, y-intercept, and there's my graph. And then the final question, explain why y equals 2 is a horizontal asymptote. Well, to find horizontal asymptotes, we let x go to plus or minus infinity. Okay. Now, since we're going for this particular one, we're talking about the graph going infinitely to the right and approaching 2 here to be an asymptote, yes? So we only have to consider going to positive infinity. So let's think about this. Y equals 2 minus 1 over e to the x. And all I did is I rewrote this function with a positive exponent. And what happens as x goes to infinity? Well, as x goes to infinity, this denominator gets really great. 2.78 to the 1,000 is a huge number. 2.78 to the 10 billion is a ginormous number. And 1, or any number, divided by a ginormous number goes to 0. So we can say that as x goes to infinity, y goes to 2. And that would be a decent explanation. All right, that is it. I am out!